One of the underlying principles of engineering in general is being able to take real-world systems, model them effectively, and then determine what parameters we can modulate or control to determine the output, um, or maintain a value within a certain level. And so that's kind of what this next series of videos under the guise of process dynamics and control is really going to discuss, is how do we effectively model the world around us in given, the various physical systems that we've learned how to study thus far in undergraduate chemical engineering. And with that knowledge, let's take that, let's insert it into a model, and then move from a steady state scenario to an unsteady state. And then furthermore, the end of this should be, how do we actually modulate or control that system, right? What kind of methods can we use to effectively control that system? And what does that really look like in terms of a process setting? So the first set of these part of videos is going to focus more on the process dynamics side. In other words, here's some chemical systems. Let's derive some equations that we've probably learned in previous classes on how these systems function, and what variables are important to us, what's going to affect something else. And then from those equations, the second half of the course is going to focus on, okay, we know what is going to change what, right? We know our inputs, we know our outputs. So now let's change into being able to figure out, how do we control an input to give a desired output. And so that's what the entirety of this course is attempting to describe. So, like I said, we're going to start out with something very, very simple in terms of a process model, and just kind of get us used to the idea of simulation. And then from that, we're going to take it and we're going to do a little bit of control here in prompt 2 to start to kind of give us an idea of where we're going in the course. And that's what this video is going to really do, is just these two prompts here. And these two prompts are really simple. They should look like something we've seen before, right? So we're given a cylindrical tank with a hole in the bottom, and what we want to do is we want to determine, from an initial steady state volumetric flow input, what is the liquid level or the liquid height in the tank going to do if we change that steady state input to an unsteady state, right? So that's all we're going to look at here. So we're going to start by simply deriving the differential equation for this system, and then we'll attempt to simulate it a little bit. So we're just looking at prompt 1 here. Did not create a straight line at all. I'm just looking at prompt 1, which is going to just be one tank. So again, here's our tank. It'll look something like this. Right, there we go. And so what that is trying to describe is that the cross-sectional area here, right? So this area is going to be a constant because it's a cylinder. So we'll call that area of the cross-section. Similarly, we're going to have a hole in the bottom of the tank, and there's going to be some fluid flow out of that hole. And we're actually given what is the area here of this hole. And then what are we attempting to measure? We're attempting to measure some sort of height. So that's going to be h, height. And we're also given some sort of flow input. So this will be Q in to some extent, right? So then this would be Q out, which would make sense. And so now we can start to see our material balance here, right? This is a pretty simple one. So our material balance, we're going to say, we're going to go ahead and assume that the density of the fluid is not going to change, right? So, for example, we should say that the change in mass with respect to time is going to be how much mass are we putting into the system minus how much mass are we taking out of the system, right? That's the material balance plus accumulation, right? Let's call accumulation Q here, big Q. So that's our typical balance, right? For any time. Now, if we go ahead and pull that mass term out a little bit, it might be a little bit difficult to envision mass here. So what we're going to do is we're going to change mass into volume. So how are we going to do that? Well, that's going to be the density times volume, right? Is mass. And that's going to be equal to density times volume metric flow rate in minus volumetric flow rate out. And for this system, we can go ahead and assume away our accumulation. And so that'll look like that. Oh, we should have a row here as well, density. And so the density of the system, because it's a liquid, is going to be incompressible, which means we can assume density is constant. Means we can pull density out here. And then we can go ahead and cancel out density like so. The other way that I've been kind of writing this, I'm using two kind of notations here. Let me go ahead and specify that if I ever write v dot, that's the same as lowercase q. Both of these are going to be some sort of volume per time. So it's some sort of volumetric flow rate that I'm trying to get at with both of those nomenclatures. I may interchange them a little bit, so apologies on that confusion. Okay, so now we're going to go ahead and derive the equation for the change in volume with respect to time, right? Let's pull that down here. So we know volume is going to be the area of the cross-section in the tank times height. So we know volume is going to be area of the cross-section times height. That's how much liquid is going to be in the tank, right? And so that'll be whatever's coming in. So this will be, again, V dot in or Q in minus what's going out. And so what's leaving the tank, we know by Torricelli's equation that we can describe that as root 2GH times the area of the hole, right? And so that's just a simplification of Bernoulli's, whereby we are bringing a velocity term here and an area term here. Obviously, velocity is going to be in meters per second, or distance per second, right? And this will be meters squared. So you can see that if we're multiplying that together, we're ending up in the volumetric flow rate units as well. Okay, so now we've kind of derived our equation here, and the only other thing we might want to do is pull area of the cross section out of this differential, right? Because it's going to be constant for this tank. And we could even actually divide that across completely if we prefer. We could say 1 over area of the cross section times what's coming in volume wise minus what's going out. And that's, now we've gone ahead and derived our change in height with respect to time, right? Now, the thing to notice about this equation is the kind of issue that we have in that we have a differential equation here that is nonlinear, right? So the height term has, actually I should rather denote that as AH there. The height term is underneath that square root, so it's being multiplied to the 1/2 power, which is not any sort of linear coefficient, right? So how are we going to go ahead and solve this then? Knowing that we have, you know, the values that we were given in the prompt, which include area of the cross section, 2 values for the volumetric flow rate in an initial steady state condition, as well as a new non-steady state condition, area of the hole, and obviously G we have. So here, what we're going to want to do is we're going to want to find an initial condition for H, right? So what will the height be at the beginning of the simulation? So during steady state. Well, of course, during steady state, our change is going to be equal to 0. And we could also lose our cross-sectional area term, which means that what's coming in is going to be equal to what's going out. Which implies that H naught, I'm denoting it as that as the initial condition, is going to be equal to V dot in over area of the hole squared divided by 2 times G. All of those are given values, so that is an appropriate way to find our initial steady state. So now that we've gone ahead and done this, it might be of interest to us to go ahead and simulate the system. And when is it going to assume steady state once more? So we can do this by 2 methods. These are both numerical methods that we're going to use here. We're going to use Euler's method first, which is a really easy discretization of the equation. And then we're going to move on to using a more robust Rado method in Python. So let's go ahead and start here in Excel. I was so smooth it almost looked like it was a cut. Or so janky it almost looked like it was a cut. So let's go ahead and call this varying liquid height. Or we could say height as a function of time for constant cross or tank. How about that? And I'm going to call this what my course name is for it. And with that, go ahead and hit save. All right. So let's code this out real quick. This is going to be pretty straightforward here. So, givens, we have a Q in steady state, we have a Q in non-steady state, we have a cross-sectional area, an area of the hole, a G. What else do we have? So this should be 9.8 meters per second squared. This is going to be 0.2 meters squared. This is going to be 1 meter squared. meters cubed per second, and 0.1. Okay, so then let's go ahead and box all that in. So our initial condition here is just going to be exactly what our formula was. Let's go ahead and name these variables real quick. Perfect. So we can say this is going to be a Qn divided by the area of the hole squared divided by 2 divided by G. Nope, that didn't come out right. Divided by 2 divided by G. Interesting. Okay, so now we have an initial height here in meters. Insert, box that in. I think that's right. Volume in up. This should be our steady state value, right? There we go. So then Euler's method. Euler's method is just a really distinct discretization here. So let's say, let's go ahead and find a delta t here. There we go. Oh, put 2 of them in there. So delta t, this is our discretization for seconds. So then this will be our time step, and this is going to be just our ordinary numbers, or natural numbers, excuse me, here. Let's go down to, what, like 30 seconds. And then this will be our actual time. So it's just going to be our time step times delta t here. So then let's go ahead and call this delta t. I don't know if I remember to name that one, so let's name that one delta t, and delta t. Let's see if I can pop that in here. Okay, maybe not. Ah, well, seemed to lock in. Perfect. Okay, so that's our actual time, right? This is what iteration of the function we're going through. This is our h at our current time, so here it's going to be h naught. And then we need a delta h. So our delta h, nope, delta h, perfect. Delta h is going to be just the function we derived, right, times our time step iteration. So it should be, what should it be? 1 over cross-sectional area times q in minus q out, which is going to be area of the hole times square root of 2 times g times the h of this step. Perfect. So then h at the next step, h at this step times h at that step. We just need to multiply all of this by the time delta here. There we go. Perfect. And so we can see pretty clearly, right, as we get toward the end of this simulate, well, even really when we get right here, we see that it drops off how much height is changing really quickly. So let's go ahead and graph that real quick to get an even better explanation here. Perfect. So we'll call this h of t for single tank, And we could format this more if we cared more. But right here, it's really easy to see that our change is happening at point 0, and the system starts to adjust. And because we have an output in that hole, we're going to find a new steady state at some point here. So it's about maybe 1.5 to 2 seconds in, we find that steady state, right? So that's pretty simple. That is a way to simulate the system. The difference is that obviously there's going to be really slight discrepancies as we change delta t, right? So that was really small, but if I did that, okay, so we can see that we're not going to achieve what we want to here. We're going to have to drag this way further down, basically run our simulation for much longer here in order for this to work. And these guys are going to have to run all the way down. A little too far down. Let's see, where did I stop you at? Okay, there's 74. Okay, well, I screwed up the graph. Should just be something like that. Okay, I really screwed it up. My point is that there's going to be round off error, right, in our values as we change our discretization. So delta H is focused on delta T, which was just kind of an arbitrary, albeit small value that we chose, but our precision isn't very succinct here, right? And so there are different numerical methods we could employ to this same function. And so to do that, let me zip you on over to Python. And Python has a function in it called solve IVP. So from its SciPy, I believe the optimize library. Let's go ahead and import NumPy as well, and some sort of plotting function, probably subplots, import make subplots. May not have, I don't think I was supposed to put those there. Oops. Okay, it was. Okay, import from plotly.subplots, import make subplots. Oh, maybe it's not even that. From SciPy.optimize. Okay. Where's this function at? Solve IVP. Solve IVP SciPy.integrate. There we go. All right. Good deal. So, what we're going to go ahead and do here is define our function. So dh dt. Take that as what? Really as a function of time and height, maybe. So we could say, we could just return qin minus np dot square root 2 times 9.8, which is G times H here. Need to find Qn somewhere. There we go. Okay. So that defines our change in height with respect to time. And so now all we're going to do is provide the salt function. Let's go ahead and calculate H naught again. We said that was going to be the steady state volumetric input, which was 0.1 divided by the area of the hole, 0.2. That's going to be squared, and then divided by 2 times 9.8, which is G. Again, I'm not coding out all the variables here, but we could do that like we did in Excel. It wouldn't be too hard to change. So then what we're going to do is we're going to call solve IVP. We're going to input the function that we're trying to solve. Now we have to give it a time span. And it tells us that the time span is a 1D independent variable. So it should just be some time here. Okay, time span is a 2-membered sequence interval of integration. So we can go from 0 to 30. Now we're on our initial condition, which is H naught, and then our method, which we want to make red dow. If that runs. Maybe I have to capitalize the R here. Okay, so solver reached the integration interval. That's great. Call that our solution. And so here are all of our values here. Here are all of our heights, right? And so we could say our height for plotting purposes is going to be that. Our time for plotting purposes is going to be that. Go ahead and take a look at sol.t. So that is simply a bunch of points from 0 to 30, which is what we told it to run. So now it's time to go ahead and create our plot here. So plot equals make subplots. Then we say, what do we say? Plot.add scatter. We can say x equals t plot, y equals h plot, mode equals points, maybe. See what that does. No, markers. Okay. And we got a whole lot of nothing. Let's see, we can make width equal to 400, height equal to 600, and template equals plotly dark. And that's an underscore in between. See if that even changes it. Okay, well that's really ugly. So we make width 800. Okay, that looks pretty nice at least. So now we just have to see what's really going wrong with the plotter here, because we don't have our points really showing up. So let's see. Okay. Say rows 1, columns equals 1. Okay, that didn't change it. So perhaps it's the fact that it's an array and not simply a list. Okay, so those plotted out appropriately. So we just need to go ahead and make these lists somehow, rather than arrays, which I think is how they're being stored right now. So that's an array, we just want to make the list. So Python function to turn 2D array into 1D list. I was going to say flatten is going to be it. np.flatten. Okay. Maybe it's not that. Let's see. Dot flatten. Where'd you go? Okay, so let's see what that does. Sol dot y dot flatten. Okay, so that made it a 1D array. Let's see if it takes that in. Flatten. I guess I could have just called the first row as well, and that would have worked, huh? Oh well. You're watching me problem solve in real time here as a coder. Okay, so still no points. What happens if I just call the first row? Oh, that's because I didn't. Aha. So now we're getting some points, even though they appear pretty odd. So for some reason it appears that our height is decreasing across the tank. That's not what we want. I wonder if this dot flatten is doing something odd. What if I just call row 0 here? Oh, so that's simply one value there. very, very close. I can feel it. Okay. So, it's not really what I want. Really what I want to do is I want to take this array and I want to make a new list. So there's a .to list, okay. .to list. .to list. Still nothing here. So it is simply a list of the values. My points just aren't showing up at all for some reason. My H plot also appears incorrect. I didn't multiply it by 1 over the cross-sectional area. Perhaps that has something to do with it. 1 over cross-sectional area was literally 1, so times 1 over 1 is not going to change anything. We are getting the right H0 value. It appears after that we're not getting anything correct. Square root, we forgot to multiply by the area of the whole here. There we go. So now at least our H plot is correct, even though it's not plotting onto the plot correctly. It's very odd that we're not getting markers here. This blue's not a color we can do. Okay, x equals t plot, y equals h plot. We gotta be close. this? Well, aha, found you. Okay. So the problem here is that it picked points in T-plot. T-plot has a lot of points near its in between 0 and 5, I should say. So rather than doing that, we could really just make our own array here. We could solve this as a lin space from 0 to 30 with 100 points in between. Okay, so there we go. Right. Looks pretty similar to the other one now, after a bunch of time. So we are back in kind of our steady state space here. Ooh, that looks terrible. Okay, so there we go. We've simulated the response after struggling to work this plotting function. So there we are. That's prompt 1 here. Oop. Okay. Now, prompt 2 talks about having 3 of these tanks in series. So, height of the liquid level in the third tank, though, what we're going to do is try to actually control it. So, using some of the fun of this course and methodology, we're going to try and control it. So, what we're going to do is we're just going to put a simple proportional controller on there, and that's just a P controller with gain KC. And then adjust the value of that gain to where the oscillations appear to neither grow nor die out. And we'll talk about a lot of that later. So the gain is going to just be multiplied by what is the set point minus the actual height, right, in tank number 3. So let's go ahead and I'll do a tiny little bit of derivation here, but there's really not much because the equation is the exact same as before, right? In the sense that we're using the same physical principles to describe this system. So I have 3 tanks in series now. They all have the same constant cross-sectional area. Right. Okay. Well, how's that? Right. And again, what we're looking at in each tank is height of the liquid, which is going to vary between the 3 tanks. So we might want to call this one height 1, height 2, height 3. Well, similarly, we would call this Q in, not maybe, Q in 1, Q in 2, Q, well, see, this is where it gets a little icky because we're calling it Q in 1, Q in 2. Well, really, what are they? They're Q out 1, Q out 2, right? Q out 3. And again, pretty easy to recognize. dH1 dt is going to be Q in naught minus Q out 1. We're assuming that they have, these tanks all have the same size outlet hole / outlet pipe. And so for all of them, no matter which tank we're at, Q out for tank I, we can say is going to be area of the hole square root 2GH of tank I. So in this case, for change in height 1, we would just say that that is going to be equal to, oh, again, cross-sectional area. Don't forget that, even though it's 1, so we can't really forget it here. Lost myself there. So we can rewrite this then for tank 1 as the following. There we are. How nice. And so then, well, what if we want to talk about tank 2, or more generically, tank I, right? Well, what's coming into a tank if it's not tank 1, right? So we can say I has to be greater than 1 in this case. We know what's coming in is what's going out of the last one, so area of the whole of the last tank, the square root 2GH1 minus, so again, this is going out of 1 into 2, this term, minus what's going out of 2, well, Q out 2, or in other words, area of the whole times root 2GH2. Pretty simple. So again, generically, this would simply be HI minus 1, HI, right? I think that makes a pretty clear sense to us at this point. And so now what we're kind of doing is we're kind of doing a little bit of a backwards control here, right? I shouldn't say that, but the way we approach this in our mind should be a little bit backwards, right? The input that we're able to adjust is going to be Q in, not, right? And we said initially it's going to be at some steady state. Q in not at steady state is what it was in the last one at 0.1 meters cubed per second, right? And so then at steady state, we can go ahead and solve for, hey, what would the height of the liquid in tank 3 be? Well, it would be again, we would just use this equation, and I is going to be equal to 3, so we would say AC dH3 dt equals area of the hole square root 2GH2 minus area of the hole root 2GH3. Okay, good enough. And again, we're trying to find what is this at steady state, given only basically an initial Q naught. We also know area of the cross section is 1 meter squared. We know area of the hole, regardless of the tank, is going to be 0.2 meters squared. So we just want to find our initial heights here. Well, we can say that this is going to be equal to 0, right? There's no change. And so then area of the hole is also going to fall off here. And we're simply going to be left with root 2GH2 is equal to root 2GH3. Square both sides and divide by 2G. We can see that H2 is going to be equal to H3. And again, that should be equal to H1, right, by induction. We could go ahead and write that out, but I won't here for the sake of time. So, and we already know what H1 is at steady state, right? We are given from the last problem that that's just going to be Q in steady state, Q in not, I should say steady state, over area of the hole squared over 2G, right? And so we know that's going to be our height for all 3 tanks initially. Something's slightly bothering me about this, but we'll just see if this ends up affecting it appropriately. So we have a system here, and it's very repetitive. So let's see what happens if we attempt to go ahead and control it. Again, what we're going to say is that H3 is going to be, what is it? It's going to be 20% higher. So it's going to be 1.2 H3 naught. So let's see if we can figure this out. Okay. So let's start at the very beginning. Let's just hard code in our variables again. So area of the cross section is 1 meters squared. Area of the hole is 0.2 meters squared. Q in steady state is going to be 0.1 meters cubed per second. Q in is going to be equal to 0. Well, that's actually what we're solving for, right? We're going to see how that responds. So then, let's see, H naught, which we're saying right now, assuming I'm doing this correctly, is going to be the same for all 3 tanks. So we're saying that's going to be equal to Q in steady state divided by area of the hole squared divided by 2 times G. And again, it's going to freak out because I haven't defined G yet. Okay. Perfect. Okay. So then H set point is going to be 1.2 times H naught. Only for tank 3 though, so hopefully we won't overflow anything in the process. Okay. Wonderful here. So now what are we going to want to do? Let's go ahead and start by defining our functions. Again, T and H, I believe that's all I put in the first time. Perfect. And they're going to return, well, the first one's just going to return Q in naught minus Q out of 1. Q out of 1 is going to be what? Area of the hole times square root 2 times G times H. Right. And then Q in naught is going to be, initially it's going to be a steady state, and then once we add our controller, Okay. So we want to actually, let's do this a little bit more logically. So we're actually going to add in an array of h's. And what we're going to say is that h1, h2, h3 are h's, right? So then q out 1 will be h1, q out 2 will be exactly this, just for h2, right? And then same thing for q out 3, h3. Now, we are told that Q into the system is Q in naught plus Kc times H set point minus H3. So now we define a couple more things here, right? Q in naught is the same as Q in steady state. And then Kc is going to be the value that we adjust. Kc equals, let's call it 0.1 for right now. I have absolutely no idea what this value should be. But this is controller gain. Okay. And what are we going to return? We're going to return an array, or a list rather. Q in minus Q out 1, Q out 1 minus Q out 2, right? Changing height of height 2, Q out 2 minus Q out 3. And so what are we really returning? We're returning change in height 1, change in height 2, and change in height 3. Okay. So, I'm not sure that this is the most efficient, so apologies to computer scientists, but I do think that this is a way that makes sense to me. And so now what we're going to do is we're simply going to do solve IVP dHdt plus series, just to differentiate from the one above it. Okay. A time span again. So let's say 0 to 100, whatever. And initial guesses. Okay, so now our initial guesses are for each height of each tank. Again, we're just going to guess H naught for all three. Method should be equal to Rato. I think we want dense output to be equal to true. What is that going to do to us if we do that? Well, hopefully something good. Alright, so it did solve it. Let's go ahead and call that our solution 2. Okay, so now solution 2 dot y. Okay, so again, here we have what? An array with 3 columns in 1 row, I believe. Okay. Now, how did we get these in the plot the first time? we said to list. Actually, what I'm going to want to do is I'm going to really want to take these and put them into so a couple things here. We want to make sure that we're actually hitting our set point. So that's what we're going to do by creating this plot. So let's say plot 2 equals make subplots. Rows equals 1, columns equals 1. We could make this into multiple subplots. I'm not going to here. But let's just copy all this because otherwise I'm probably going to screw it up. Plot 2, plot 2. Okay. Okay, now we need each plot 2. Let's actually split these into H1. H1. We'll do this for all 3 here. H1, H2, H3. Okay. Now we're going to watch me fiddle around with indexing here for a second. So sol2, too many values to unpack. Let's look again at the shape of sol2. Oh, that's because we need to look at y. 3 by 8, so it's 3 rows and 8 columns. Okay. Okay. Why is it 8 columns? Well, for some reason it is just going through 8 times here from 0 to 100. If I can put another 100 and see if that does. Okay. So we're going through 8. That's what we got for right now. So let's call this H. Let's see. I don't know how to do this quickly, so apologize again to the computer scientists. I told you we were going to futz around with indexing for a second here. Interesting. So now it's telling me I'm out of range. Oh, that's because I'm simply looking at the shape. I don't want to look at just the shape. I want the entire object. Aha! Now we have you. Okay. So actually make this into the lines here. Alrighty. So here we go. Now we can start to see, right? And this makes sense. I don't really know how to add a legend here, but if I did, I would say that trace 0 would be tank 1, trace 1 would be tank 2, trace 2 would be tank 3, right? So first thing we want to do here is look at HSP. So that is 0.015. We can see that we're not even close to that with this gain value right here, right? So let's up the gain a little bit and try it all over again. So now we're going up a little higher, right? Try it again. Okay, even higher, but you can see that we're still running into about the same height here. Let's bump it up even more. Okay, still a little bit higher. 1335. Okay. So now we're hitting a peak, but it's starting to come back down, right? Interesting. If we make it 5. Alright, so now we're getting up there, but we're falling right back down, right? And we're getting limited here at about 0.014. Again, what we want is this value here. Let's actually see if we can add that into one. Plot 2 dot add scatter x equals what? Y equals HSP. We can't do that. Okay. That's alright. Alright. Bump it up even more. Alright, now we're getting pretty close here. Even more. Now we can see. So we're starting to get some oscillations in here, right? And if we go back to our problem statement, it says adjust a value to where the oscillations appear to neither grow nor die out. So oscillations are dying out, right? As we approach this value. So let's keep going. That's too high. Okay, oscillations are dying out. You see we're getting continuously closer to that value here. Okay, we have an error. This value in the square root is apparently getting hard to calculate. Okay, it's solving there. Oh, whoa, okay. So now we have oscillations barely growing. And now we just have oscillations, right? And so now we've hit that value. Again, we're calling that value ultimate gain. And we'll talk about that later when we go into tuning. But this is kind of the ultimate gain for this system, right? You can see that if, you know, maybe we hit the exact middle of this system here, we'd have about 0.1 or 0.015. And again, that's what we're really looking for, is this value. It's kind of right in the middle of these oscillations. If I were to draw, you know, the line that might be like the 0 for this sinusoidal wave, it would be pretty close to our set point, right? And that's exactly what the controller is doing is it's saying, hey, there's a difference between the set point and, the actual value out there right now. Let's go attack that. And let's go see how we can adjust that. And the bigger the difference between the set point and the actual value, the more change that the controller is going to implement. It's a very simple feedback control. And so, as we can see here, the controller is obviously working. It's doing a bunch of work in moving up and down, but we're not getting any closure in actually maintaining the liquid height that we're wanting, right? We actually have the height going lower in 10.1 than what was the initial steady state height with a lower input rate, right? So our controller is working in the sense that it is doing work, but it's not working in the sense that it's getting us the desired output. So that's kind of the question that's going to come up, or one of the questions that we need to solve in this course is, well, how do we fix that? And so we'll tackle that later in this series. For now, that's all for this video. I'll see you real soon in the next one. Bye-bye.